Well, thank you. It's a great pleasure to be here. I had the opportunity about 11 years ago to spend a sabbatical at the Weizmann Institute with Reshef Tene, and I have very fond memories, and I look forward to coming back in person in the not too distant future. So today I'd like to tell you about our work on graphene and its applicability to energy storage. So I'll start with just reminding you what the different carbon allotropes are, how we make graphene, how we process it, some sensor and transparent electrode work, and then our work on laser scribe graphene and supercapacitors. So first of all, I think we probably all know that graphene is a single layer carbon, but what you might not have thought of, it's the last form of carbon to be discovered. Of course, if you stack it up, you end up with graphite. Graphite was discovered in the Middle Ages. But in more recent times, if you take 12 5-membered rings, you get fullerenes. Here's carbon 60. And that wasn't discovered till the 1980s. And then if you roll up graphene, you get carbon nanotubes, and that was discovered in the 1990s. But graphene wasn't discovered till the 2000s. So even though carbon goes way back, graphene is pretty new. Here's a little bit about past work. I'll tell you about our early work on intercalation exfoliation. Of course, we probably all know about Novosov and Geim, who peeled pyrolytic graphite with Scotch tape and went on to win the Nobel Prize in physics for understanding the physics of graphene. But there's other ways to make it. Walter de Heer's group at Georgia Tech took silicon carbide and they heated it up and they drove off the silicon, leaving a layer of graphene on the surface of silicon carbide. If you want electronic grade stuff, you think about chemical vapor deposition, and Rod Ruoff showed us, oh, let me grab a laser here to make this a little bit nicer. All right, we've got a laser pointer. So if you think about chemical vapor deposition, you can heat methane or some other form of carbon to 1,000 degrees, and with a little bit of hydrogen present, you can deposit it on copper. And you can grow this single layer, and then you can etch away the copper, you can put a photoresist on, and you can end up with graphene. And so if you want to make electronic grade graphene, that's probably the way to do it. And Johnny Coleman showed us that you can actually exfoliate graphite directly in liquids. The yield is very low, but it is a way to make more of the material. This is my favorite picture of pyrolytic graphite. So this is a piece about the size of your thumb. And this is from Neil Bartlett's lab where I did my postdoctoral work in the mid-1980s. And what we're doing here is we're hitting this block of graphite with a laser. Now, a normal material would heat up in 3 dimensions, but graphite certainly is not a normal material. And as we probably well know, heat conducts by 2 different mechanisms. One is phonon modes, in other words, the chemical bonds. And in graphite, the sp2 carbon is all bonded in plane. And heat is also conducted by carriers of electricity, in this case, electrons. And so those are all due to the pi overlap. That's also in the same plane. So if you hit it with the laser here, if you were to touch over here, you'd burn yourself, but the top is still cold. So we're looking at heat conduction in 2 dimensions. And this is the only picture I've ever seen of a molecular scale property in real 3-dimensional space. So it's kind of an interesting look at low dimensions. Now, in the year 2000, so this is 4 years before Novosov and Geim did their work with Scotch tape, one of my colleagues came over from mechanical engineering. His name's Tom Hahn. And he said to me, he knocked on my door and he said, I heard you're a resident expert in carbon and I want to know, can you make a single layer of carbon? And I said, I probably could do it, but why would you want it? And he said, everybody's using carbon nanotubes to reinforce polymers. And there's a problem with that. He said, if you want to reinforce a polymer, you need a 2-dimensional object, not a 1-dimensional one. And he showed me the mechanical calculations he had taken out to prove it. And then he said, how would you make a layer of carbon? And I said, well, graphite's a layered compound. It's been known for about 100 years that you can intercalate it. I said, so I just intercalated with something that was reactive and exfoliated. He said, that's great, you got to do that. So we heated graphite with potassium. There's a well-known reaction. It makes something called KC8. And between every layer of carbon goes potassium plus. And this material is quite reactive. So you can take water or alcohol, and if you expose it to it, it literally exfoliates. It blows apart the layers. So we did this with alcohol under controlled conditions, and then we just sonicated, and it scrolls. And if you look at this picture, this electron micrograph here, a TEM, you can see the TM grid, but this is a carbon nanoscroll. And you can see it's so thin, you can see right through it. You can see the lacy carbon grid. And here's a more tightly wound scroll, and here's a whole lot of scrolls. So our goal was to make graphene, and we believed we had made graphene. So we took out a patent on this in 2002, 2 years before graphene was discovered. And we published this paper in Science in 2003, showing that when carbon gets very thin, it scrolls. Now, what did Novosov and Geim do? Well, they showed that with Scotch tape, if you keep peeling back and forth, eventually you get to a single layer. What's interesting is what they really have is, it turns out the Scotch tape is critical, because without the Scotch tape, graphite simply, or graphene simply restacks to form graphite, or if it finds itself, it scrolls like this. However, we realized that this method, although it does make single layer graphene, it also makes 2, 3, 4, 5 layers, all different combinations. And so we realized after Novosov and Geim did their work that this probably isn't the best way to scale it. But what is a good way to scale it is something called graphene oxide. And this is very old chemistry. It goes back 150 years. Here's a paper from the 1860s. I guess it's now 160 years. So the idea is if you take graphite and you oxidize it, and you can do this with nitric acid and potassium permanganate. What you do is you take the graphite and you put in carboxylic acid, hydroxyl groups, and epoxide rings. And the material disperses in water. Now, what disperses in water is not a conductor. It's actually an insulating material because we disrupt some of the conjugation. But if we could deoxygenate it, we could get back to graphene. By the way, if somebody does have a question, you're welcome to stop me. All right, so what I'm going to do, yes, please. No. Okay.
Rick, sorry.
Yes.
I had a question. On the previous one where the scrolls roll on themselves, the reason that they don't remain flat is because they have some different tension on the two sides, or what's the reason for that?
So basically, it's the sonication that causes movement, right? So these are in solution, in this case, just in water. And as soon as they find another piece of graphene, you end up with the dipole-induced dipole interactions, and they start to scroll. So it's just simply a lower energy state as it replaces the liquid. Just like I'll show you that if we evacuate the material, we just pull it through a filter, these pieces of graphene just simply stack up. And instead of getting graphite, what you get is graphene paper. So it's just simply, graphene by itself is not stable. Either it finds another sheet of graphene and starts to graphitize, or it finds itself and forms scrolls. Or if you have Scotch tape or some other surface, it will stick to that surface. Okay, so I'm going to show you that we can take graphene oxide, we'll make graphene paper. I don't have time to tell you about electronics, but I will tell you briefly about sensors, graphite oxide foam, lithography, and energy storage using supercapacitors. So first, a little bit more about graphite oxide. The first thing we did is we reduced it chemically. We just used hydrazine. And so this is chemically reduced graphene oxide. It disperses in water. And I call it a dispersion, not a solution, because it shows the Tyndall effect. The Tyndall effect is if you take a laser, in this case, we're taking a red laser. If this were a solution, the laser would go right through and you wouldn't see any laser light. But in fact, you see the red laser light. And the reason is because this is a dispersion. There's individual graphene sheets floating around in the water. Now, why do they stay as a dispersion? Well, they all have a negative charge on their surface, so they stay away from each other. How do we know that? Well, we can get rid of the charge using any salt. So if we throw in sodium chloride, it flocculates out because we just knock out the surface charge. And we know it's graphene because it has all the attributes of graphene, being carbon and being very thin. So if we look at atomic force microscope of the pieces that come out, if we run a trace along here, you'll see about a 1 nanometer step height. And people have decided that's graphene. Okay, and I'll point out that we published this with my colleague Gordon Wallace in Australia. I happened to do at a Fulbright Fellowship a number of years ago. And this paper has probably become one of the most popular in this area. So it has over 8,000 citations today. Now, I mentioned we can make graphene paper. How do we do that? Well, we just take a solution of chemically produced graphene and we pour it through filter paper. And if we use plastic filter paper, when we're done, we can literally pull this off. So this is graphene paper. Now you may say, well, how does that differ from graphite? Because graphite is just stacks of carbon. But graphite's actually three-dimensionally ordered. It has an AB-AB stacking. This has totally random stacking. So we just take thousands of sheets and stack them together, reforming van der Waals interactions. And you can see this stuff's pretty strong. And you can see how smooth it is. You can see reflection in it. We tried to use pure hydrazine because we thought we could make even better graphene instead of aqueous hydrazine. So we took the material, the chemically reduced graphite oxide, and we put it in pure hydrazine, and it makes a dispersion. And now we can get rid of almost all the oxygen moieties. And when we do that, we made at the time the largest pieces of graphene that had ever been made chemically. And if you look at this, this is an SEM picture on the left. Here's an AFM picture on the right. And I think if you stare at these for a moment, you'll say they're the same picture. Now, I originally had funding from DARPA, which is the Defense Advanced Research Project Agency. And I showed these pictures originally at a conference at UCLA. And my program manager looked at this. There are about 25 people around. And he said, well, Rick, this is really interesting, but there's a problem. And I'm like, what's the problem? He said, something's missing. I'm like, what's missing? He said, Florida. So if you stare at this, this sort of looks like the US, right? And here's Los Angeles where I am, there's Texas, and there is no Florida. So we learned from that program managers actually have a sense of humor. All right. Now, we can actually do science with this. So we ran an AFM probe along white, along red, and along blue. And what you'll notice is as we go over this step height, each of these heights is about 0.6 nanometers. Now, it turns out the interlayer spacing in graphite is 0.34 nanometers. And if you multiply that by 2, you get 0.7 nanometers. So we know for sure that this is not 2 layers of carbon. It's actually 1 layer. Now, you may say, well, then why don't we get 0.34? Well, it turns out that we didn't do this. We did this experiment on silicon, and the silicon is not a perfectly smooth surface. So we probably should go back and redo this on freshly cleaved mica, but it's hard to convince your students to go back and do that. But anyway, I just wanted to show you, this is one way of showing that we have single layers. Of course, there's many others. There's Raman and so on. Oops. Now, another thing we can do with graphene is we can combine it with carbon nanotubes. And so we did this. This is with my colleague Yang, who's an expert on things like memory devices and optical devices. And what we wanted to see is what happens if we put this in hydrazine as opposed to chlorobenzene. Chlorobenzene is a pretty good solvent for carbon nanotubes. But you'll notice that after 1 hour, everything's still stable in pure hydrazine, but it starts coming out of chlorobenzene. And in fact, here's 12 hours, but this is stable for months or probably years. So hydrazine is a really good dispersing agent for these. And once we disperse them, we can put them on any substrate you want. So here we spun them on glass, and you can see the faster you spin them, the thinner the layer of graphene and carbon nanotubes. Put them on sapphire, you can put them on plastic, you can put them on silicon. Okay, we're most interested in the plastic. Why? Because my colleague's interested in solar cells. And so right now for solar cells and other electronics, your cell phone and so on, indium tin oxide or some derivative of it is used as the transparent conducting electrode. But we're interested in flexible electronics. And so ITO is, you really can't bend it. So we took ITO and we put it on plastic. And then we put our graphene carbon nanotube thing on plastic. Polyethylene terphthalate's the stuff from soda bottles or drinking water. And we're looking at a current voltage curve. So with our material, we get the same conductivity as indium tin oxide. So you can see that here in this IV curve. Now we put it on plastic, and the reason is then we can bend it. So we just simply bent it 10 times back and forth. And of course, the indium tin oxide on plastic loses conductivity. It drops about 3 orders of magnitude. Why? As you bend it, you break up the crystalline domains. On the other hand, the graphene carbon nanotubes, you can bend all you want and nothing happens because they're molecular materials. So you can really think about using these things for transparent conducting electrodes. I have another colleague, Bruce Weiler, who's an expert on sensors. And so he asked me if I could put some graphene on a micro hot plate. And he's particularly interested in these because then he can heat them up. So this is a silicon nitride material. And so here's a little piece of graphene we put between his interdigitated electrodes. And from this, he was able to do a lot of sensor work. Now, I want to just show you the band structure of graphene. So graphite would have a valence band and a conduction band that slightly overlap. But graphene, if it's perfect, has this direct cone that meets at a point. And so this is the filled valence band. This is the empty conduction band. So these are the pi orbitals that are filled, pi star that are empty. Now, if you dope it N-type, what you're doing is you're adding electron density to the pi star orbitals. And so that should increase the conductivity. Conversely, if you p-dope it, you remove electron density from the valence band. However, that should add holes to the valence band and should increase the conductivity. So in fact, perfect graphene cannot be used as a sensor. But we're not actually making perfect graphene. We're making graphene with a little bit of oxygen because we make it from graphite oxide. And so what I'm showing you here is our material, our graphene from graphite oxide. We're looking at normalized resistance versus time. We're bringing up ammonia, which is a good electron donor at 5 parts per million. And every time it sees some ammonia, you'll see the resistance goes up. So what are we doing? Here's our material that we're starting with. It's already slightly oxidized. And what we're simply doing is adding in electrons. So what we believe is we're filling in states in the valence band and the resistance goes up. We're making it less conductive. Now, if that's true, I should be able to withdraw electrons and see the inverse effect. So here we go. NO2 withdraws electrons at 5 parts per million. And every time it comes in, we bring in NO2. We're lowering the resistance. In other words, we're increasing the conductivity. So what we think we're doing is we're p-doping a little bit more, making it more conductive. Now, I know some of you work on sensors and you're probably looking at this and say, these are the worst sensors I've ever seen. We have a sloping baseline, things are changing. Well, that's where micro hot plates come in. So we can just simply heat this up to about 150 degrees. And we do that, then we get a nice stable change in resistance at 5 parts per million. And when we sent in a paper, the reviewers liked it, but they said, you know, we can smell ammonia and we don't know why we want to detect NO2. So give us something we should be interested in. So we looked at 2,4-dinitrotoluene at 52 parts per billion. And you can see even at this parts per billion level, the signal to noise is quite good. Now, why should you be interested in 2,4-dinitrotoluene? Well, actually, if you think of the main explosive used in the world, trinitrotoluene, TNT, it always has some dinitrotoluene as an impurity. And the vapor pressure of this is around 700 parts per billion. So if you can detect this at this low of level, you can actually use this graphene sensor to detect explosives. So there might be some promise in graphene and its sensitivity. All right, I'm going to shift gears a little bit here. And I want to show you, this is graphene oxide. So we freeze dried it. And I'm just going to light this on fire. And let's see if I can, I think I have to get rid of my pen. Oops. Try this. Here we go. Okay, we're going to light it on fire. And what you see is this material burns, but it's deoxygenating. What's left is still carbon. It's just giving off carbon dioxide. And now we're going to take graphite oxide paper and hit it with a flash from a camera. All right, so what we're doing here is it absorbs the light, it gets hot, and it blows off CO2. Imagine controlling this reaction. Well, how can we do that? We can do that using something called Lightscribe. And Lightscribe is a $25 device that you get and you can put in your computer stack. It's comprised of a 780 nanometer laser, a magnifying glass, and a very sophisticated computer program that allows you to raster any image. So the first thing we did is we just put graphite oxide, hit it with a laser, current potential. So graphite oxide is an insulator, hit it with a laser, convert it to graphene, it becomes a conductor. And you can see this better if you look at this film. So this is a piece of plastic. We put graphite oxide on it, it's this golden brown material. We hit it with a laser and we can draw interdigitated electrodes or whatever patterns you want. So this is an insulator, that's a conductor. We then paid an artist for a picture of a person with a computer for the brain, and we reproduce this in laser scribe graphene. So the dark part is graphene produced from graphite oxide, the light part's graphite oxide, and the stuff in between is partially converted. So you can see you can get pretty decent resolution just with a very cheap laser. And we made sensors. So here's interdigitated electrodes. And just to show you that they work, this is room temperature, 20 parts per million of NO2. And every time it comes in, you'll see that the resistance drops. Now, I had a graduate student who actually came from Egypt, and I'll show you a little bit more about him. And he came with a master's degree in electrochemistry. And as soon as he saw we made this stuff, he said, oh, I'm going to run a cyclical tamagram. And he came to my office and he said, you're not going to believe this, but the peak separation for a one electrode oxidation is 0.059 volts. And I said to him, you're right, I don't believe you. He's like, what do you mean? And I said, well, you probably know that my PhD was with Alan McDermott and Alan Heeger, who went on to win the Nobel Prize for the discovery of the first conducting polymer. So I got to work on polyacetylene, which is what they discovered. But I said, what you probably don't know is what I really did for my PhD is I worked with a group and we built the first batteries using this conducting polymer. And I said, I still remember the Nernst equation. And I know that in theory, a perfect one electrode oxidation, the peak separation is 0.059 volts. And I said, so you can't get that. It's a kinetic experiment. And he told me I was wrong. He went down the hall and he grabbed an electrochemistry book and he came back. And here's the Nernst equation right here in the middle. And there it is, 0.059 volts. What I didn't know, but he did, is it goes out to 2 more digits. And so when he measured this, there it is, 0.059 volts, but the next digit is a 5. So it's really is a kinetic experiment, but this is about as close as you can get. And from this, we can calculate the speed of moving charge. In graphite, it's 1.3 times 10 to the minus 4, but in our laser scribe graphene, it's 1.3 times 10 to the minus 2. So basically, we can move charge around 100 times faster in our laser scribe graphene. So as soon as he did this experiment, it became obvious we should be trying to store energy. And while we were doing this, after we published this paper, I got contacted by a group from Newcastle, England. And they said, we're paying a lot of money in order to make electrochemical sensors. And what they're buying is edge plane pyrolytic graphite, and it costs about $200 a piece. And they went through a lot of these and they said, could we make these electrodes using your technique? And I said, probably. So we collaborated, we made these electrodes, and when they measured the peak separation, they got 59 millivolts, exactly the same as what we got in our experiments, and faster than these very expensive edge plane pyrolytic graphite. And of course, they could make a lot of these and just cut them out and use them. So it's a cheap tool for doing that. What's probably more important, though, is energy storage. And I don't need to tell you, if we're going to have a green economy, the sun doesn't shine all the time, the wind doesn't blow, so we got to store the energy. And when you need your laptop or your cell phone, often they're not charged. Or if you're driving your electric vehicle, if you're going from, in my case, from Southern California to Northern California, right now you've got to stop for a several-hour lunch while you recharge your car. So we think we can solve a lot of these issues. Now, I want to remind you that power is how fast you can deliver something, and energy is how much you can store. So a capacitor is very high power, but low energy. A battery is fairly high energy, but low power. And so what we want to do is combine the best of both worlds and get a supercapacitor. And I took this from the Maxwell website. Maxwell Technologies is the leading supercapacitor company in the world. They were bought about 1.5 years ago by Tesla, because they have some technology that Tesla needed. Supercapacitors are already $1 billion business. They back up cities for power. They're used to turn windmills. Batteries aren't fast enough to respond to do this. And in many ports, especially in Asia, when they take these containers off of the ship, when you put it back down, you can get over 40% of the energy back if you have a supercapacitor. A battery can't respond fast enough to do that. There's now a fleet of electric buses in China that run completely on carbon-based supercapacitors. So this bus is filled with supercapacitors. It can go a mile or two, and every mile or so, there'll be a charging station. As people get on and off the bus, they're simply charged up. And these buses run 24/7, 365 days a year. My favorite is this. In Europe, in a train station, there is a revolving door connected to a supercapacitor that runs the lights in the restaurant. So this is human-powered energy. Now, one technical slide. This is called a Rogoni plot. It's power density in watts per kilogram versus energy density in watt-hours per kilogram. So capacitors are really high power, low energy. Batteries are over here, high energy, low power. And so what we want to do is go in this direction on this Rogoni plot. And this is the goal for electric vehicles by the US Department of Energy. What's interesting is graphene could, in theory, solve this problem by itself. It has a very high theoretical specific capacitance, about 550 farads per gram. Trouble is, if you actually go, so here it is on this chart, but when you actually go to make these devices, you only get about a quarter of that, about 100 to 150 farads per gram. And the problem is the restacking of graphene. So the surface area of a graphene sheet is 2,630 meters squared per gram, but that's assuming you can address the top and the bottom of the sheet. If you put two sheets together, you lose half the surface area per gram, so it dropped to 1,300. And so until we did our work, there was no way that people could figure out how graphene would not restack when you stuffed it into an electrochemical device. So here's how we did this. We took our CD, we put a piece of plastic, we coated it with graphite oxide. We hit it with a laser, but this time we tell the laser just darken the whole thing, turn it all to graphene. We peel it off, we cut it into pieces, and we build a cell that really looks like a battery, right? 2 electrodes, an electrolyte, or a separator, we add a drop of electrolyte. But supercapacitors are a bit different than batteries. Instead of an anode and a cathode, we have a positive electrode and a negative electrode. When you charge this up, the positive electrode takes on negative ions, the negative electrode positive ions. Because they're already there, they only move atomic distances, and so you can charge this in seconds. So if I haven't gotten your attention yet, this is the one slide you want to look at. So here we told the laser just to draw stripes. And so this cartoon is, we start with graphite oxide, we draw a stripe, laser scribe graphene. And here's what it looks like under a microscope. So graphite oxide is this beautiful layered compound. We hit it with a laser, it absorbs the light, it gets hot, it blows off CO2. And when we're done, we've created a fractal. Now, this is our form of graphene. It's completely different than what Novosov and Geim are making. Novosov and Geim with Scotch tape are making the world's best graphene. We're making the world's most effective graphene. But if you're going to do energy storage, this is exactly the structure you want. And the reason is you need a structure that's incompressible and you can address all surfaces. Now you may say, wait a second, how can you call that graphene? It doesn't look like anything like I thought. Well, graphene has 3 attributes. It's pure carbon. So even in air, we can get 99% carbon. It has high conductivity, we get that. And it has high surface area. So I mentioned a single layer is just above 2,600 meters squared per gram. We measure between 1,500 and 2,000 meters squared per gram. So we're at the single sheet level, not the 2 sheet level. And the reason we don't get the theoretical value is this is connected in 3 dimensions, and that helps us with high conductivity. It also means you can compress this all you want, and without extreme pressure, you'll still have the attributes of graphene. All right, so here's activated carbon. That's what's used in current supercapacitors. Here's our laser scribe graphene. And I'll skip the things, but I'll show you it's completely flexible. So this is a change in resistance on bending, and you release it, it goes back. You can bend it 1,000 times, it doesn't care. You get the same resistance. So you can make flexible electronics. Graphite oxide is an insulator. This is a current potential curve. The After we reduce it to laser scribe graphene, we get a textbook rectangular wave. It's pure capacitance. And so we can compare it to current materials. This is stack capacitance in farads per cubic centimeter versus current density. This is a commercial device in blue. Our device is about the same. As you run them harder, the current device falls off. Ours is still performing above 4,000 milliamps per cubic centimeter. So graphene is a really good material. You can charge it fast. You can discharge it as fast as you like. This is one technical slide. We looked at the frequency response. And what's interesting is we can compare this to commercial materials and aluminum electrolytic capacitors. So first of all, a commercial material, which is made from roasted coconut shells, have a time constant of about 10,000 milliseconds. Our material is over 300 times faster. We're at 30 milliseconds. And an aluminum electrolytic capacitor runs about 1 millisecond. Now, if you look at electronic devices, these are the bulky things in electronics. And so if we could get our speed down to 1 millisecond, we could actually think about replacing bulky electronics with flat things. And I'm going to show you that we're working in that area. And in fact, one of my former postdocs is a professor who's working on this very problem. Okay, so how do we address this problem? So we're working on something called carbon nanodots. And what this is you can take organics like citric acid and urea, you can microwave them, and you get these little dots that are pretty close to pure carbon. So here are the dots. They center around 1 nanometer. They have a little bit of size difference. They have different functional groups depending on what you used. So they might have some nitrogen, they might have some oxygen, and so on, depending on what you used. So we published a paper a couple of years ago in Advanced Materials. It's been a very highly cited paper. People are interested in these carbon nanodots. But what we're interested in using them for is to repair graphene. And so what we did is we've made this, and we've shown that these materials now are down at 0.29 nanometers. Let me show you this. So what we do is we take our graphite oxide, we put our carbon nanodots, we hit it with a laser, and if you look under a microscope, you'll see this. So here's the graphene produced from graphite oxide. There's the carbon nanodots. And it actually lowers the amount of defects. We can see this in the Raman. This is the D to G peak. G is the graphitic peak. D is often considered the disorder peak. And as we put more of these carbon nanodots, we actually improve the graphene. And we've run the time constant down. And as I said, we're down below 1 millisecond. And this is work done by Ari Bornstein, who's now a professor at Ariel University. Okay, so we can get down to 0.29 milliseconds. Now, going back to our supercapacitors, we can make very flexible supercapacitors. So we take these. This is a current potential. So this is just, we're simply running this experiment. And what you'll see is as we flex this, the curves overlap with each other. And we made a little movie just to show how flexible these are. So what we're doing is we charge this up for a few seconds. We can run an LED. And now we're going to flex this graphene supercapacitor, and you'll see it doesn't affect the LED. So you have flexible electronics. And for good measure, my students took graphene oxide that they reduced to graphene, and they use it as a conductor. And you can flex that too. So you can make graphene conductors, you can make graphene energy storage devices, you can put these all together. Now, you may wonder, well, how do we run electronic devices? So if you look at the back of your computer, it doesn't run on 1 volt, which is our aqueous cell, or 3 volts, our organic cell. It runs on 14.4 volts and about 4,400 milliamp hours. So how do you get there? Well, what you can do is you can put devices in series. So we took a 1 volt aqueous device, we put 4 in series, and you get out 4 volts. We put 2 in series and 2 in parallel. We double the voltage. Here's 1 volt. We doubled it to 2, and you'll notice the area under the curve is doubled. And if you've seen these before, you look for an IR drop here, and there's almost none. So these are really good devices with very little internal resistance. They have very good cycle life. This is 10,000 cycles. You'll see the capacitance retention is good. They have good shelf life. We ran these for 4 months, and you can see very little loss. So what's the problem? Well, the problem is if you put them on a Rogoni plot, they're better than any commercial supercapacitors. And if you go to ionic liquids, they start approaching rechargeable batteries, but they're not there yet. And of course, we'd rather do aqueous or organic cells. So then the question is, how do you increase the energy storage capacity? And I'm going to show you one way to do that. And you asked where people need to go. Well, what we need to do is we need to create supercapacitors with higher energy density or batteries that respond faster. And people are working in both areas. I'll show you how we do this. So one way to do this is to take a material that is a pseudocapacitor. And so manganese dioxide is the material, if you look at any battery that you have, primary battery, like a AA or C battery, it's all filled with MnO2. And if you go, we have these dollar stores, you can buy 10 of these for $1. So you can imagine the amount of manganese dioxide in your battery is worth less than a penny. So this is really cheap stuff. However, it's an insulator. So if you get a C battery or AA, it's filled with about 40%, 40% carbon black to make this conduct. And the carbon black is not electrochemically active. So our idea is replace it with graphene. So MnO2 by itself has over 1,000 farads per gram. You just can't get that. And so what we wanted to do is put our graphite oxide and put the manganese dioxide in our laser-scribe graphene. And so we can do this electrochemically, we can do it chemically, and depending on how we do it, we can control the amount that we put in. All right, let me show you the results. So if you look at this, you can see the graphene that's produced, and these things that to me look like cauliflower, that is the MnO2. And we can look by photoelectron spectroscopy, and you can see the carbon, you can see the manganese, you can see the oxygen, so it's completely throughout the material. And we can even demonstrate that it's in the correct oxidation state. We have the correct form of manganese dioxide. And when we look at these, we get very high capacitance, higher than anything that's been seen. And in fact, here's the result. So if you look at a current potential curve, you get these beautiful rectangular waves. And I'm going to focus at the bottom right. This is the specific capacitance of MnO2 versus the amount of MnO2. So in theory, manganese dioxide could have 1,370 farads per gram. Now you can't get that because it's an insulator. But if we put 10% MnO2 and 90% graphene, we can get around 1,200 farads per gram. So we can get most of it. But what's much more important is if we go the other way. So if we go to 5% graphene and 95% MnO2, we're still at about 500 farads per gram. And that's the beauty of graphene. It doesn't take very much. You can use it as a scaffold and you can put other materials in. MnO2 is one. There's many other metal oxides that are even better than MnO2, and you can put any of them in that you like. But this is a good proof of principle. All right, another thing that I wanted to show you is we can make miniature devices. And why do you want miniature devices? Well, if you have a pacemaker or a radio frequency device or a hearing aid, we need little tiny power sources. And so you can get micro batteries or you can get micro supercapacitors. And we decided to just take these interdigitated designs from the literature and reproduce them. So on one of our films, we just told the laser to make 100 different interdigitated electrodes. And so you can do this in about 20 minutes or 30 minutes. And we have all these interdigitated electrodes, and you can see you can do this pretty well. Okay, how are these going to work? Well, we did some with 4 interdigitated, 8, and 16. And of course, the more you do, the closer together they are, the better they are. And they're flat, and you just put a drop of electrolyte. And if you look at the stack capacitance, as you go to 16, you get really good capacitance. These are the charge-discharge curves. There's low internal resistance. There's a little tiny IR drop. But the stack capacitance is very good, and these work out at 20,000 milliamps per cubic centimeter. So, and they're much better than commercial devices, which fall off, and they're better than other things that have come before them. And in fact, if we look at a Rogoni plot, power density versus energy density. So again, aluminum electrolytic capacitors are high power but low energy. Lithium thin film batteries are high energy but low power. And here's our different supercapacitors. And if we go to an ionic liquid, we can get something that has the energy storage capacity of a lithium thin film battery and the power of an aluminum electrolytic capacitor. And so this just shows you what you can do. It also may tell you that lithium batteries aren't necessarily the best way to good at scaling down, but you can make very high powered devices very simply. All right, so hopefully I've convinced you that we can use this laser scribing technique to fine tune pattern graphene, write sensors. We can make supercapacitors. We can combine metal oxides. We get what are known as hybrid electrodes, and we can get very high energy density for supercapacitors. We can mass produce this, and if you're interested, we've written some reviews, graphene for batteries, supercapacitors, and beyond, and design and mechanism of asymmetric supercapacitors. But what I really want to show you is a group from NOVA, this is the public broadcasting service, came to my lab to film. And they made a video of our process. And in a few minutes, they can show you better the process than I could ever explain. So we're going to take a look at this.
There's a lot of talk about renewable energy, but how feasible is it? A major barrier, believe it or not.
Oops, sorry. I didn't mean to do that. I'm going to try this again. Okay.
There's a lot of talk about renewable energy, but how feasible is it? A major barrier, believe it or not, is battery storage. And that's where something called supercapacitors come in. They run on static electricity, and they're capable of recharging and delivering power faster than batteries. But they don't store as much energy yet. Enter chemist Rick Kaner. You see, supercapacitors are limited by the surface area available for holding electrons. And Kaner's developed a technique to produce electrodes with lots of surface area out of graphite.
This is what graphite looks like as it comes out of the ground. It's a mineral.
And this is what's in a pencil.
Absolutely. So a pencil is nothing more than graphite combined with clay. So this is the material that's used in essentially all batteries as at least one of the electrodes. So the question is whether you could make this in a high surface area form. And that is where graphene comes in.
Graphene is the strongest material ever tested. It's a layer of carbon that's 1 atom thick, giving it extremely high surface area. Kaner says 1 gram of the stuff would cover 4 football fields.
Graphene provides the high surface area and conductivity necessary to store large amounts of charge.
Which means graphene might just allow supercapacitors to be even more super. And Kaner's lab has come up with a surprising way to make it. It starts with plain old graphite. This is a chunk of graphite oxide that was mixed with water and then freeze-dried. Maher El-Kadi hits it with an ordinary camera flash.
Big flash.
Yeah, it's big. So just watch what's going on.
Okay. Oh,
The pulse of light's converted to heat, burning away the oxygen and leaving behind graphene.
that's graphene right there?
So what's left over, we call it now graphene foam.
Kaner's lab has developed a system to print exact designs. A layer of plastic gets coated onto the surface of a CD with a solution of graphite oxide. Once dry, it's inserted into a CD laser labeler.
Oh, that's wild.
But instead of doing its usual job of etching a label, wherever the laser hits the dried graphite oxide, that spot's transformed into graphene.
Oh, I like this technology.
Aside from a graphene likeness of David Pogue, El-Kadi's printed 2 graphene electrodes.
Obviously, there's a huge worldwide market for CDs with pictures of me in graphene, but I'm guessing that these are more important to the future of mankind. You've etched circuits out of the graphene?
Yeah, so these circuits are basically micro supercapacitors. And this stores as much charge as these like very bulky capacitors that you will find in any electronic device.
You mean this totally flat pattern right now could hold as much charge as this capacitor?
Yes, and we actually made them store 1,000 times more charge as this size of a capacitor.
If we could scale this to the size of electric vehicles, then you could actually, instead of pulling into a gas station, you'd pull into a charging station, and within minutes, your car would be ready to go.
An electric car that you can charge as quickly as it would take to fill up?
I would definitely like to see that happen, and that's exactly what we're working on.
Wow.
All right, with that, let me thank the people who have done this. You just met Maher, and we founded a company called Nanotech Energy, which is actually trying to do this for real. And I also want to mention Ari Bornstein, who's an assistant professor at Ariel University, and we introduced the carbon nanodots that he worked on. I've had funding. Maxwell Technologies gave us some money. The National Science Foundation and Nanotech Energy has been a great supporter. We've also recently developed a electrolyte for lithium-ion batteries that's non-flammable. And so with that, let me thank you for your attention, and I'm happy to answer any questions.
Thank you, Rick. This is really an amazing talk. And I have a few questions, but I want to leave first the floor to everybody wants to ask questions. Just unmute yourself and ask the question.
Rick, I have one question or two questions.
Please.
One question is, you start actually from graphene oxide and you burn it and you get graphite, but you still have a lot of oxide there or defect there that will control the charge. So I can understand that for supercapacitor, it doesn't really matter. But if you want to have it for sensors, you need to control the Fermi level. How can you control the Fermi level with so many defects?
Yeah, so I think you make a good point, and that is that we can get rid of almost all the oxygen, but we're talking about, 99% carbon, 1% oxygen. And so if you're going to make a really good sensor, you're right. It's not going to do that. But it actually, the sensors are pretty, they're sensitive. I showed you can get down to parts per billion of sensitivity.
Yes.
What they're not good at is they have no specificity. And so if you want the specificity, you either have to add other groups, or what you really need to do is make an electronic nose where you have not one sensor, but an array of sensors, each good for something else, and looking at a neural network kind of situation. So I agree with you. This is yeah, go ahead.
I have a second question. You are so smart to separate the graphene from each other, the sheets from each other. You're a great chemist. You can tether some moieties to the graphene in order to make it a protrusion that will not stick to the other piece of graphene. Can't you do that?
Well, of course, we're very familiar with your work on cutting about transition metal dichalcogenides. And so I'm sure if my colleague had come to you and asked, could you make a single sheet of carbon, you would have given him the same answer that I did. So cutting it apart is easy. Reassembling it or preventing it from reassembling is very difficult. And that's the beauty of the Scotch tape that Novosov and Geim used. In fact, I'll tell you a story. Konstantin Novoselov was visiting us, and I was out to lunch with a group of people, and I said, I was curious, everybody uses graphite and Scotch tape, but nobody imagined that you could get down to a single layer. I said, how long did it take a poor graduate student? How many weeks? And he said, no graduate student, it was me. I spent 5 weeks working at it. And I'm thinking of that, a chemist would never do that. Only a physicist who believed that they could get down to a single layer. And then if you get a single layer, how would you know that you had a single layer? But they were pretty sure that spectroscopically they could pick it up. And they were right. I mean, it was just, yeah. So I think it's an interesting problem. And what I like to do is say the beauty of what they did is it's great for electronics. But if you're going to do energy storage, you need to make, you can't make pieces of this. You need to make kilograms and ultimately tons. And so the only way to do that is by chemistry. And that's why the beauty of graphite oxide is it's cheap. It starts from graphite. We just oxidize it with common materials. And then it's how you get back to the graphene that is critical. And for energy storage, we don't want perfect graphene. We want this defect, this 3D fractal that goes down to the atomic level. And that's what we get. And so I am absolutely convinced that the next generation of energy storage will use graphene. Now, what I can't tell you is, will it be my graphene or will it be somebody else's graphene? Because there are many ways to get to this same sort of material. And they all have different defect levels. They all have different impurities. So what you're getting at is a very critical point.
Thanks.
Other
Can I ask a question?
Yeah, I have a question. Back to the question of Tene regards sensors. So usually in sensor we are planning to sense very low, say, let's say level of gases, or let's say low concentrations. For you show the NO2, you show the ammonia, etc. However, and this is like based like on this graphene flakes. However, like so it means that if you change a very tiny change in your flake composition, or let's say dimension, okay, you change totally the sensor. So it means, can you say something about how much these sensors are repeatable? So you can build one sensor and it's very nice and you can get very low concentration, etc. However, can you repeat this for mass production industry, for example?
Yeah, so I'll tell you that in the lab, we can make a number of sensors that look the same. But when we decided to start a company with these materials, we very quickly decided that we were not going to build sensors for just the reason you say, because we can make them cheaply, but to make them absolutely reproducible and so on is difficult. So we took out a number of patents, but we have never pursued sensors as a viable thing as far as industrial use goes.
Asher, I think you have a question.
Yes, thank you. As far as I understand, energy storage capacity is because there is the electric breakdown. When you take the voltage around too high, it will simply break and you lose the capacitance. So can you tell something about the electric breakdown limit in the capacitors that you suggest?
Yeah, these materials, so I need to distinguish between what we're doing, which are supercapacitors and ordinary capacitors. You know, in ordinary capacitor, if you take two metal plates and you have a dielectric, at some point it will break down and you know, often it's hundreds or thousands of volts. But what we're doing is using these for energy storage. So these devices generally are only going to on the order of 4 volts. And they use an electrolyte. And so it's the electrolyte that breaks down. And so if you go to an ionic liquid, you can actually go to 4 volts. There's some ionic liquids that you can actually push it to 6 volts or so. We would like to go to higher voltage because unlike batteries, which are limited by the energy density due to the redox properties of the material, a supercapacitor is only limited by the voltage. But the voltage is not the breakdown voltage like in a normal capacitor, it's the voltage of the electrolyte. And so most ionic liquids, 4 volts, there's some now that are pushing 6 volts, but they get expensive. And so we usually just focus on either aqueous electrolytes to make it very cheap, or non-aqueous, and we can get just 3-volt devices. So it's a good question. It's just not, we're not pushing the limits of that because we have this electrolyte in our supercapacitors.
So it's 4 volt along what kind of thickness? What is the?
Oh, I see. Yeah. So you can think of these working on a very small scale because basically every surface is addressed by the electrolyte. And so that's why you can charge these things extremely fast. That's why you saw, you know, I was showing 20,000 volts per centimeter squared, which is quite a, you know, quite a high charging density. You can discharge these quickly, but you can also discharge them slowly if you want to. So they're very high powered devices as far as how much charge you can, how fast you can charge them up.
So you would say that you have high charge density.
You can have very high charge density. Yes, supercapacitors are very good at high power. So what they're less good at is energy storage. And so that's why I was trying to demonstrate that we can put materials that store more energy. Of course, there's a trade-off. As you store more energy, you're probably going to lower the amount of power. And so what a lot of people are doing are looking at hybrid devices. There's actually devices you can get for your car that is half supercapacitor, half battery to make something, you know, the rechargeable batteries, the lithium-ion batteries are very good at storing energy. They're not good at things like regenerative braking, which are use supercapacitors. They're not real good at, you know, if you hit the accelerator and you're trying to go up a hill. And so there are a lot of devices that use these supercapacitors to take regenerative braking and get a lot more power out of them, or to boost the energy of a lithium-ion battery.
Thank you.
Other questions?
I have kind of a follow-up question. I'm a graduate student from physics, and so I understood that you were talking about needing maybe more energy storage from what I understood, but now you're saying that maybe replacing this the liquid that goes inside, right, the tubes and the channels that the graphite after the laser hits it form, then if you replace this liquid, the electrolyte, you can actually get a very good battery super capacitor, right? You can. So was there like an attempt to make a very maybe expensive but one-time like futuristic supercapacitor that has very high power and energy?
So let me tell you what we're working on in the lab and what we're working on commercially. So commercially, we started Nanotech Energy. If you go online and look at Nanotech, you'll find that we just raised $30 million. So what are people putting $30 million into? Well, we developed a non-flammable electrolyte for lithium-ion batteries, and it works very well with graphene. And so graphene, you know, I'll put it this way. If you take a lithium-ion battery, you still have to put a lot of carbon black in to make it conduct properly. So imagine just taking that carbon black, which is not electrochemically active, and replacing it with graphene. So the graphene will conduct electricity, but it's also electrochemically active. So you get a benefit at little cost. Now, it's not zero cost because carbon black is almost free and graphene is not yet, you know, you pay something for it.
Yeah.
But you get something back. So what we're interested in is both improving batteries and then making them more like supercapacitors. Of course, in the lab, I spend most of my time trying to improve the supercapacitors that I showed you by putting manganese dioxide in, but there are many other metal oxides that are even better. There's cheap ones like iron oxide, there's more expensive ones like ruthenium oxide. And so we've shown just by putting metal oxides, you can get over half the energy density of a lithium-ion battery. And that is the goal, to compete with lithium-ion batteries without using lithium, if you can get it. And also to extend the cycle life. So these things have cycle lives. I showed tens of thousands of cycles. Some of them even go longer. Lithium-ion batteries last, you're lucky if they last hundreds, maybe 1,000 cycles. So good questions.
Other questions? If not, Rick, I have a couple of questions.
Please.
One specific and one more open-ended. The specific one was when you did, at the very beginning, you showed the graphene paper where you superpose all those graphene. So basically you don't have a stack, as you said, A, B, B, A, B, but you end up with all these orientations. So you surely know that there is lots of hype now about the magic angle, the work that Jarilo Herrera is doing at MIT and so on. So I guess that when you put them randomly, some of them will have some magic angles in there, no? So I was wondering about the properties of this graphene sheet that you get this way. Did you measure performance? Did you notice anything interesting, or are there discontinuities between the different parts of the sheets? Just as a curiosity, because I haven't played with that.
No, it's a very good question. We've never really spent much time on the graphene paper. In fact, my friend Rod Ruoff actually spent more time looking at the mechanical properties and just shown that it's very strong, which is surprising because it's just van der Waals forces, but you get enough of them together And so it's like you could, if it's thick enough, it's hard to tear. You can cut it with the scissors and so on. There must be some of these sheets at all different angles.
Hmm.
And so some would probably be at the angle of interest, but how many, I don't know. And could you influence how it stacks? I really have no idea. But it is kind of remarkable that you can just run this through filter paper and they
Right.
restack.
The other question is more open-ended now, looking at the future. So you showed this fantastic work. I love this CD thing. I would like to know more from you about how to play with it. But there are other materials. For example, in my lab, we work with TMCs and we kind of sulfurize metals or phosphorize. So there are plenty of other 2D materials these days that can be drop casted on a CD. And then you can play with the laser and so on. Have you tried any others to see what happens there?
Yeah, that's a good question. I can tell you more about what happens with the laser and graphene oxide. I haven't really played with them, and I think there's other people who have. But let me tell you a little bit more about the laser. So you can ask the question, could I take a laser pointer and do this with that, right?
Mm-hmm.
And it turns out the answer is yes and no. So if you take a laser pointer and hit it at graphene oxide, nothing happens. But if you take a laser pointer and magnifying glass, that will work. So you can write your name. So we often use a laser table. You can buy a laser table for a few $100s, and you can have a laser that you can put in a magnifying glass, and you can print anything you like. You can also ask, could you do this with a modern day Xerox machine? And the answer to that is no. It turns out a Xerox machine uses the equivalent of a 600-watt light bulb, and that will not work. What you need is about 2 milliwatts of focused laser power, and that's why you need the magnifying glass. Now, other people looked at what happens if you take a really high-powered laser.
Mm-hmm.
And the answer is you blow away most of the material, and so you end up with, you can draw very tiny lines, but you have very little material left. So we're interested in keeping the bulk of the material because we want lots of this stuff. So there's a lot of interesting questions, and I agree, anything that will absorb this light, and most materials, especially if they're colored or dark, will absorb this kind of light. And so, yeah, I think you could do this with a whole lot of materials.
In fact, let me add to this. I assume you do this in air, right? Because this CD, I guess, it's exposed to the environment.
That's
what
right.
if you're able to control the atmosphere in there and have it either in vacuum or in the presence of certain specific, atmospheres with the elements? Then you could kind of implant or dope or modify the material.
Yeah, no, I agree. I think you could do this under much more controlled conditions than we are. Which brings me to another thing. You may wonder, how did we ever do this? What prompted us to do this? Turned out, as I alluded to, I also work on conducting polymers. And one day, one of my students read an article. It was a letter to Nature. And it said, don't expose your nanoparticles like your carbon nanotubes or your silicon to laser, because if you do that, they burn up. Yeah, as Reshef knows, right? And so one of my students said, well, what if I take my conducting polymer film? We're making little nano polyaniline. And he tried it, and the stuff melted. And then, so we were doing that, and then when we started doing it with graphene, we said, well, what happens if that? So we did the same thing, and then we started using these CD discs. So I was asked, what happens if you get rid of the air? And so the interesting thing is, is the laser, somebody suggested that the laser was producing heat rather than being absorbed. So we did experiments where we put a glass sheet in between the laser and our material. It doesn't matter. The light goes through, and so it really is absorbing the light. We put in nitrogen, and it still works. So your thought is a good one. Change the atmosphere, maybe put in ammonia, see if you can dope nitrogen in, put in sulfur, urea, or something like that. But there's just a lot of space to work with. And, we're just focused on the energy storage aspects of this.
I hear. Interesting. Fascinating. Other questions? If not, since Rick, I guess at some time you want to go to sleep, maybe. So
I'm good.
just,
This was fun.
I want to thank you on behalf of IVS. This has been a great start, really magnificent talk. It has been recorded, so I assume it's okay for you if we place on our website?
Absolutely. Please,
Okay.
please do.
Thank you very much. And again, I don't know how much to thank you. It has been a magnificent talk. In fact, I will communicate with you because I have some thoughts that I would like to exchange if it's okay. And then I thank everybody who attended, and please let the people know about this amazing series. And if someone wants to see the video, Chaim will work to put it on the IVS website. Thank you very much, Rick. And
Very
thank you
good.
everybody for joining.
Thanks for the great questions.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Bye.
Thank you.